Welcome to our introduction lesson to electromagnetic radiation. Over the next few lessons, we're going to be unpacking this very interesting and exciting branch of physics. And we're going to be having a look at how it has applications in so many different ways for our everyday lives. Everything from the song you heard on the radio, to the cell phone call you made this morning, and even the x-rays done in the hospital near you are all examples of electromagnetic radiation at play. As part of this section, hopefully, you will also come to understand that not all electromagnetic radiation is super dangerous or is going to turn you into the Incredible Hulk. In fact, hopefully you'll realize that it's got many, many useful applications in our everyday lives. But before we begin, we must pose ourselves a simple question. Let's go to the board. Have you ever thought about how a reflection of your face in a mirror is always the perfect representation of your facial features? Have you ever considered why, when you stand in a very dark room, our reflection does not appear in the mirror at all? These are the kinds of questions that hopefully by the end of these lessons you'll be able to answer for yourself. Let's move on to our concept map. Obviously, as part of our investigation, we're going to be looking at the electro and magnetic aspects of electromagnetic radiation. But as part of that, we're going to be linking it to how electromagnetic radiation propagates from one place to another, and what different types of electromagnetic radiation we find in the spectrum of electromagnetic radiation. But before we get into any of that, we first need to understand electromagnetic radiation in a little bit more detail. To do that, we're going to start by examining how electromagnetic radiation can be said to behave like the waves we've already looked at as part of sound and mechanical waves, but also, and often more interestingly, how electromagnetic radiation can behave like a particle. And it is this dual nature that will form the basis of many of our interesting and unique questions for this section. Before we begin though, let's have a look at some key words to make sure we are familiar with them. The first word is medium. It's one you should be familiar with from your previous work in waves, and not one you confuse with the type of steak that you buy at your local Spur. The medium in physics is the substance through which a wave passes. It is the substance through which the energy is transferred. We also have the word energy down here, and that is because obviously all waves represent energy moving from one place to another. We need to remind ourselves that all waves have a frequency, which is a measurement of how often a particular event occurs per unit time. In the case of waves, it's how often a wave front passes a particular point in the medium per unit time. We also know that all waves travel through their mediums with a particular velocity, and this will form the basis of quite an interesting discussion on how fast electromagnetic radiation travels and how it's the fastest thing we've ever observed. Finally, you should be familiar with the idea of electromagnetic, in that all of the radiation in the electromagnetic spectrum is made up of two components, one electrical and one magnetic. So what is electromagnetic radiation? Well, electromagnetic radiation is different forms of energy. We get forms that are very high energy and can be quite potentially dangerous to us, and forms that are relatively low energy and pose almost no risk to us. We see electromagnetic radiation in all its different forms all over the place in our modern lives. We see it coming out of the light fixtures that we use to illuminate our homes. It's used by X-ray machines in hospitals to take a look inside people's bodies and see what's wrong. And as I mentioned at the beginning, it's used to transmit radio signals across our country so that you can hear your favorite song no matter where you are. As part of our investigation into electromagnetic radiation, we have to ask ourselves the questions: is electromagnetic radiation a wave or is it a particle? To better answer these questions, we need to unpack the properties of waves and particles and relate them to electromagnetic radiation to make a decision. For us to better understand the electromagnetic spectrum and radiation, we need to pose ourselves two important questions. Does electromagnetic radiation behave like a wave, or does it behave like a particle? This question and this dual nature of electromagnetic radiation forms the basis of a lot of scientific debate and will form the basis of a lot of the investigative work we'll be doing in this section. So what are the properties that both waves and particles share? Well, we already know that waves transfer energy through a medium, but particles can also transfer energy. Think about throwing a tennis ball. If you throw a tennis ball hard enough against a wall, you can hear the energy that it transfers in the form of sound, and if you had a very sensitive camera, you'd also be able to see that where the tennis ball hit the wall, there was a slight increase in temperature. That is, again, a transfer of the energy from the tennis ball as a particle through the medium that it's traveling to the wall at the end of its journey. The next property that waves and particles share is that the energy that they transfer always comes from a particular source. In the mechanical waves that we looked at earlier, like sound or waves on a string, the energy came either from your voice or from you shaking the string to create the pulse that traveled down it. In the case of a particle, like our example with the tennis ball, the energy comes from you, the person who throws it. So let's move on. In our understanding of waves, we've already looked at the wave equation. We already know that the wave equation is a means to calculate the velocity of a wave when we have its frequency. Let's go to the board for a bit more information. In the wave equation, as I said, we are able to calculate the velocity of a wave by taking the product of that wave's frequency and its wavelength. You should already know that the frequency of a wave is the number of times the wave passes a particular point per second. And the wavelength is the distance between any two consecutive points of a wave that are in phase. We often refer to a wavelength as the distance between two consecutive crests or two consecutive troughs. With the wave equation, as I said earlier, we already know that we can use it to calculate the velocity of a wave when we have its frequency and its wavelength. As we said earlier, frequency is simply how often an event associated with a wave occurs. In the case of the mechanical waves we've already looked at, the frequency is simply how often a wave front passes a particular point in the medium per unit time. We should already know that wavelength is simply the measure a measure of the distance between any two consecutive points on a wave that are in phase. We often say this could be from crest to consecutive crest, or even trough to consecutive trough. Now we need to take a look at some of the properties of waves we've already looked at and see if we can relate them to electromagnetic radiation. We already know that waves always move in straight lines. To picture this, think of again splashes in a pond or ripples in a pond. When you create a disturbance in the medium, the waves from that disturbance travel outwards in straight lines. The next property that we've already looked at for waves is this idea of reflection. We know that waves reflect, and we can see this in our everyday lives. If you ever speak into a room that is large and empty, and then hear your voice bouncing back off the walls in the form of an echo. That echo is the reflection of the sound waves back to your ears. We also know that waves are able to refract, which is the changing of their speed as they change mediums. This one's more challenging to picture in the real world, but a nice example of it is waves crashing or breaking on a beach. With waves on a beach, as the waves approach the shoreline, the shoreline rises, the water becomes less deep. This causes the water to slow down and results in that typical curling and crashing shape that we associate with waves. The next property of waves we've had a look at is that of diffraction. Diffraction is the process whereby waves can bend round an opening or through an opening and then spread out. This opening is often called an aperture in physics. A nice example of this is if there's ever been a large group of people making a lot of noise in a room. If that room has a single window that is open, you can usually hear all of the sounds inside the room, even if you aren't standing directly in front of the window. You could be above it, below it, quite some distance from it, and you'd still be able to hear the sound because the sound waves are diffracting through the opening that is the window. The last wave property that we've had a look at is that of interference. Interference is also not one that we see very commonly in our everyday lives, unless you know a little bit about the acoustics of music and playing it in a large venue like a hall or a concert venue. These large halls and concert venues are built in such a way that the sound waves constructively interfere at all the different places inside the hall to ensure that the sound sounds exactly as if you were standing right at the front of the stage, no matter where you are in the room. Now let's have a look at some of the properties of particles and try and relate them to the properties of waves we've already discussed. As you can see listed on the board, particles also travel in straight lines. They also are able to reflect. Again, think of our tennis ball example and how the tennis ball will only move in the direction of the force that's applied to it, and it will always bounce back off of an object that it collides with. But we also have observed that particles are capable of changing their speed when they move through different media. Remember, media is just the plural of medium, all right? So continuing with our tennis ball analogy, the tennis ball will quickly change speed if it hits a surface that is rougher or smoother, all right? Our tennis ball also has a mass, and that's how we are able to consider it a particle. And it is this mass that means it is able to collide with other objects. And the last property of particles we need to consider is that they are able to penetrate objects when they are projected with high amounts of energy. So, the last thing we need to do is ask ourselves a few more questions, like, is everything with these properties a wave? What happens if we can't see the properties with our eyes? And finally, the most important question for this lesson, is electromagnetic radiation a wave or a particle? Let's take a break, and then we can come back and find out.